and she was for almost 3 years, right, in Pasadena, in the group of Jason Alizea. And since last year, she's a chargé de research at CNRS in Paris, and
Thanks a lot, Federico, for being here. Yes, I don't think Federico, please feel free to interrupt any time. It's personal answer to interactive discussion. Yeah, so the main topic of today, Wednesday will be measurement of phenomena. Also, let me know if you understand when I write, because I don't write. So I will talk about measurements, especially in many-body quantum systems, meaning that I have in mind a state that lives in a usually huge hyperspace, and so the interesting physics comes out from the collective behavior that we have, and how this collective behavior impacts, for instance, the behavior of observables like entanglement or correlation functions. So before, let's say, going into the main part of the seminar, which will be more about the interplay between measurements and critical system, I would like to give an overview of why measurements have attracted a lot of attention in the last few years. Before I should specify what do I mean by measurement, and I really mean what we learned in the course of quantum mechanics. So I have a state, psi, and I project a projector, psi m, and I normalize my state with the probability, which is psi. So, for instance, if pi m is a rank 1 projector, then it means that it just this projector here like choose your favorite basis, like the z basis. M is a string of numbers, like n1, n2, n3, and L. Okay? And if you measure the z basis, for instance, each of these M can be 0 or 1. So the hyperspace in which this measurement outcome lives is the tensor product of the hyperspace in the set 1, hyperspace in set 2, so we have H1, H2, tensor product HN. So our measurement outcome is in this hyperspace, which has dimension 2 to the n, because each of these outcomes can take 2 values. And also our initial state will live in the same hyperspace. So this is what I mean by the system, and this is what I mean by measurement. Just basic definitions. And so as I was saying, this operation, when combined with some feature of quantum mechanical states, like for instance criticality or quantum dynamics, can give rise to non-trivial phenomena. So one non-trivial phenomena which has been observed are entanglement transitions. Again, these are just motivations, let's say topics in which measurements have been recently used in order to not only probe quantum matter, but really generate some knowledge phenomena. And one of these is, I think, the idea of entanglement transition, which work as follows. So suppose that you start from a very simple product state. The product state means that the initial state is basically the tensor product of a state in the first side, second side, and so on. So this is a very trivial state, where the trivial I mean trivial at the level of entanglement of functions. And then I let the state evolve with a random circuit. Okay, so let me draw this circuit. Okay, so you start from initial state, which is this product state, which is trivial. And then we apply these bilocal gates, where these gates are drawn from the unitary group of dimension D square, where D is the dimension of this qubit, so for qubit, D is just equal to 2. And these are random gates. So this is why this setup is called random circuit. Like you start from a very simple state, and then you let it evolve with this random circuit. You see it as this feature of having discretized time. And this framework has been used a lot in the last years in order to model the dynamics, because it's an example of a completely random dynamic, without any conservation of and also because using the fact that each of these gates are random, it's also a nice platform where one can do analytical computation. And so in this framework of random circuits, think of with some measurements, for instance, here, projective measurements with some probability P. P is the probability of performing the measurement. And the entanglement transition consists in the fact that if you study what happens as a function of P, one can identify a critical value of P, for which basically, if the probability of doing this measurement is very low, then one can find a volume law behavior of the entanglement. The volume law behavior of the entanglement simply means that the entanglement is extensive in the subsystem size. So it has similar as a function of that. This is a late time behavior. So I let the system evolve, and then I compute the entanglement. And this volume behavior is due to the fact that we have this unitary dynamics. And in general, when you have a system and you let it evolve, at late time, the dynamics generates a sort of thermal entanglement. On the other hand, for p larger than PC, so that is critical value, the measurement starts to play a crucial role because when we have a state that we projected, we tend to keep the entanglement of the system. Like eventually, if we do some projection on all sides, we get exactly the measurement outcome, which is simply a proper state. So eventually, the entanglement is really completely zero. And so one can find an trivial transition between a volume law phase and an area law phase of the entanglement. And exactly the critical point, the entanglement grows logarithmically. And this logarithmic growth of the entanglement is a feature of critical systems. So it's very interesting because basically you interpret, you get this transition from one law to another law passing through a critical point, whereby critical point really means that the entanglement grows logarithmically, and as we see, this is a peculiarity of okay, so this is, I think, one nice, let's say, phenomenon that can be generated through entanglement, through measurements, and due to this non-trivial interplay between UniPa dynamics on one side and measurements on the other. Another motivation for studying measurement comes more from the realm of state separation. I will make an example just to give you an idea of what I mean by using measurement as a shortcut of state separation. In general, the idea is that finding alternative protocols in order to reduce the amount of operations that one has to do in order to prepare a given state, and usually using something which is non-unitary, like in this case measurements, can be very useful in order to reduce the preparation time or the depth of the circuits that one needs to prepare a specific state. And I give you, I think, one of the simplest examples in the context of measurement-based quantum computation. So, this idea of using measurements to prepare some state. Okay, so we start from the Hamiltonian, which is the cluster Hamiltonian. Write it down and then okay, so DLS are points in operators, and you can see that this Hamiltonian lives in another system. So we call these chains 1 and 2, and we have, so for instance, Z, X, Z, we have these triangles here, and then we have Z, X, So we have the Hamiltonian that lives basically on these on the edges of these triangles. And this Hamiltonian is a very particular structure because one can check that all these terms commute with each other and they also square to 1. And if we now compute the correlation function, say, of Vj1, Vk1, this is 0. So we start from a state which doesn't have any sort of order along this direction because this relation is at 0. And however, this Hamiltonian is a typical example of an SPT, symmetry protected topological space. What does it mean? It means that there is some underlying symmetry which gives rise to a non-trivial ordered parameter. And the symmetry in this case is Z2 cross Z2 symmetry, which are generated basically by the part operator along the second and the first chain. So, one is to product of J1, and the other is associated to
the Are you imposing that this thing is true for a certain state, or?
For the ground state.
Okay, okay.
And so the non-trivial ordered parameter in this case is called the string ordered parameter, and we can write it down as follows. SJK, which is so the operator, the first line means that the operator lives on the first chain, the second line means that it lives in the second chain. This is the notation. In that case, it's very nice why one should choose this single ordered parameter, because basically, as I said, in the ground state, each of these terms commute with each other and they always go to 1. So you think that all of these terms are exactly 1. And then you have to multiply a set of them in order to reconstruct this single ordered parameter. So I have this one is Vj2 x j plus 1, 1, z j plus 1, 2. Then I multiply by z j plus 1, 2, x j plus 1, j plus 1, z j plus 2, 1. So this is equal to 1, and you remain with x and x, leaving only the first chain, which are these x and x here. And then you continue in that case. So this is how you can construct a single parameter for this specific state. So this is 1. And this is 1 because of these, it's basically what is captured in non-trivial SPT that we have. So now we want to do measurements on top of this, on top of the ground state of this cluster Hamiltonian, and see what we get. And for instance, we can do measurements in the X basis in the first chain. Okay, so here.
So, you said that this overbody is always equal to 1, with 1 in some phase.
In the ground state.
So, the other so if it's an overbody, it means that parcels on the line.
So it can acquire, I think it's exactly equal to 1
That's
in this specific Hamiltonian. You can have some terms that still preserve the symmetry, and then this get but in this specific Hamiltonian, it's called, I think this is called the zero correlation length in the cluster Hamiltonian. But you still have some terms that preserve the symmetry, which is
It's how to an integer value, or it's
no, it could be smaller than 1.
What is this topological?
It's symmetric under, you can think of two parity symmetries, one associated with the first chain and the other associated with the second chain. So we have these two cross-into symmetry, and the correlation that captures this non-trivial structure is so it doesn't have long range order as we have for the Majorana chain, for instance. This correlation function is 0, but you can find an non-trivial order parameter which is able to capture this non-trivial.
But there is no topological environment that captures the phase whether or not.
No. No, it's because there is no like parameter here. Like I think one should change.
Oh, yeah.
And yeah. So this is really just for the here. So we have this cluster Hamiltonian. We take the ground state and we perform measurements in the X basis on the first chain. So projective measurements. And so it means that we have inside the ground state. And we apply the projector.
Sara, what do we know about this ground state? Just that this is uncorrelated, or?
Well, this is what I know. This is 1 and this is 0. Here you can compute all the correlation function you want. I think this is the only one. It's usually a starting point of doing this measurement based on computation because it's an easy state to prepare. I think if you start with some product state and apply control Z gate, it's easy to prepare with one layer of circuits. That's why it's a reference point, just because it's easy to prepare. So you take a state which is easy to prepare, and then you perform measurements. And let's see what we get. So the measurement this is our cost management state, where MJ can be plus minus 1. And we want to compute the properties of this psi element. Actually, you can already imagine what happens if you just look at your single parameter. Like I'm saying that I'm setting equal to 1, all of these operators here. So if you just do this trivial replacement, you can see that you're getting a state where the two-operation function on the second chain is 1. And these are the typical correlators with the state. Let's try to see more explicitly. So, if we compute DJ 2, from this state, one can check that these so it's the product of all of the measurement outcome. And so if you choose all the measurement outcome equal to 1, this is exactly equal to 1. Another way, if you don't want to do this hardcore selection and just take a random measurement outcome, is to consider that something like sum over all the measurement outcome, K of them, Zj2, Zk2, M, and weight all of these correlations with this thing here. So Mj plus 1, Mj plus 2, Mk. So now if you plug these results here, since these are outcome plus minus 1, they also go to 1, and the sum of probabilities must be 1. So this is also 1. And so basically, the idea is that you started from something which was you start from something which was exactly 0, then you perform projective measurement in this case is in the first chain, and you get something which is which has Zj1, Zj2, Zk2. Quindi di calcolare le esistenti. So this is the easiest way to prepare the DC state by simply preparing this class Hamiltonian and then doing measurement, let's say, on this first chain. Okay, so basically, I hope that I've convinced you that measurements can be used to do climate issues in physics, or more in the realm of environmental solutions, by exploiting the competition between unit dynamics and projective measurements, or in the realm of quantum state preparation. Do you have any questions, curiosities, or doubts?
Maybe one more question. So here you get, if I understand correctly, the GZ on the second line, right? So you,
On the other
like, instead of the other one measured, so on the other way. And you get it unconditionally to the measurement outcomes, or you say for every measurement outcome I get a GZ line, still possible different cases?
Yes. So, okay, if you do cross selection, then we get exactly one. Or for generic measurement outcome, you can use this trick of averaging all of these correlation functions with this thing here. You can do a third step actually, which is applying what is called the decoder. So, okay, so basically I measure, okay, with this state, and then apply the unitary operator. So I apply the unitary operator, U of M, slide M, where this U of M takes this form. So it's a product of the J, and J2. So basically, this is it's a stream of accelerator that depends on all the size that you have measured and all the measurement outcomes, which gives you as a, once you apply these on these, it gives you as an output basically this one. And so if you so if you do now you get the square of this.
So it's basically a calculation procedure, right? Or
more or less, yes. Just that the calculator is a bit more.
but depending on the measured outcome, you get a unitary on the other side that depends of course on the measured outcome.
Exactly. Yes.
And it's local.
Yeah, so, I mean, yes, in the interpretation protocol, there is one measurement output for which you don't need the correction. Also, in this case, there is one measurement outcome, which is when all the sides are equal to 1, all the outcomes are equal to 1, but you don't need it. It just becomes identity. Yeah, exactly. We apply a unitary operator that corrects all these outcomes. I mean, finding this unitary operator is not trivial. I mean, it would be nice if for any method that you do, we know what is the decoder that allows us to get feedback, let's say, of the measurement outcome. Here, of course, it's simple. It's not the typical implemented by the system. Okay, so now that I think we'll agree that measurements can make something interesting, let's enter more into the details of what I've been doing in the last years. Can you raise the... Reasons now, and I'm trying to use measurements to prepare critical stage. Like you start from the stage which is already critical, and then you prepare another critical stage. But then the dependence on the measurement outcome. Okay, so. So we've seen environment transition, we've seen continuous separation, and now I will describe this concept of measurement after criticality, meaning what happens when you perform measurements on the ground state of critical systems. And the reason for which I think this question is interesting is because, as you will see, critical systems are very particular in the realm of UniPa systems because they are characterized by some long-range behavior of correlation function, but not as long-range, let's say, algebraically decaying correlation function or logarithmic growth of the entanglement, as I was mentioning before. And they are particularly sensitive to external perturbations. So one can ask, what happens if I do a measurement? Where do I go? What do I get once I perform a measurement on a state which has already some structure and it's so sensitive to perturbations, to external perturbations?
Still with the goal of preparing certain states, or just like seeing what happens?
See what happens, yes. Then you can also ask, can I use measurement starting from a critical state and getting another critical state? Okay, so in order to introduce the concept of measurement after criticality, I also have to introduce a new kind of measurements that one can do, which is called weak measurement. Because we think of taking a critical system, or whatever state actually you want. We cannot simply apply a projector, right? Because if I have a system and apply a projector, I get a product state, like this string of outcomes, and this state is trivial. So I want something which is non-trivial, and this is why I wanted to introduce the concept of measurement. Usually, someone is familiar with the concept of with the literature of the environment transition, this concept of weak measurement will be okay, so in order to define a weak measurement, one can define, in order to use weak measurement, one can define a cross operator. So this is a Krauss operator. What are the properties of this Krauss operator? It satisfies the completeness relation, meaning some LJ is the measurement outcome. This can be a polymetrics Z, X, or Y. And lambda basically is telling us how far we are from the projective limit. Indeed, so for lambda equal to 1, we get an ordinary projector. And for lambda smaller than 1, we really have a weak measurement, like a softer version of a projector. This is the Krauss operator that involves
We need just special case, right? I guess in general, measurement doesn't need to have that specific structure without measurement or operator, etc.
Yes, but I will focus mainly on local measurement of single site measurement of power.
And with lambda you said close to zero or just generally small?
Later we will see that we are really using the regime of lambda close to zero. Because it's where the measurement becomes weak, like close to the identity. And a usual way in which this cross operator is rewritten is applied side by side. So basically, as a product of the KJ, is the following. So start from side. The genetic state is the genetic state. And then we get post-measurement state, which is nomination, e to the beta, sigma j, and j, sigma j alpha, acting phi, and beta is the basically the idea is that side by side, this we can expand as cosh beta plus nj sinh beta, and then so it's cosh beta sigma j alpha sinh beta and j. And so you can identify these two terms here, and in this way you get the relation between and this is usually the typical form that one finds at least in this literature of measurement hypercriticality. You have a state side, and then you perform a critical state, and then you perform a weak measurement, so software version of the objective measurement, and you ask what are the properties of this state in the regime of small beta. By small beta, in the regime where we still have access to a fictitious description of the model. Now, an interesting question to ask at this point is how do we perform this? Like, what is the way to perform a weak measurement? And there are several ways. So we've seen now a protocol which is based on the use of some ancillary degrees of freedom. And tomorrow we'll explain, let's say, more experimentally friendly way to implement weak measurement in the context of okay, so I'm reading that. Okay, we start from two systems, or better, one system, we call it psi, and some ancillary degrees of freedom, psi A. And the first step is just a tensor product between psi and psi A. Okay, so this level, we have two systems which are the cathode and the cathodes. And here actually it's nice to be able to use some aesthetics of freedom because it gives some sort of not to prepare different kind of measurements that may be like not only this kind but also for generic measurements. So at this point, I will specify what kind of aesthetic field we have and what kind of system we have. So I'm trying to explain how to do that with how to realize the connection. So I got it. And I was needed to introduce some ancillaries of freedom. So the first step is just to consider the tensor product of these two functions. Then the second step consists in entangling these two wave functions. So you apply something which is product of J, acting on side A, and then we call it and this J we get the form into the REU. Then we have an operator J acting on the system, and then operator J acting on the system. I didn't actually say. So I and not going sideways. And okay, so for instance, small u will be the energy C, no? Because the small u means that we have a small amount of entanglement between the two chains, and we see these measurements. Let me do the third step, which is applying a projective measurement, say by M on side U, and this really say product over J and J and J side U. So now I measure basically the ancillary side by side. Okay. And then we ask what are the properties of this post-measurement state. And by properties, I really mean entanglement or correlation. Correlation. Of divided by let me define this way. So this is psi A, and then we have product over J, bracket J, and J, and J, and J, psi A. This is it's called work probability. It's the probability of extracting that as an combination. So you can see already here that in order to have something which is non-trivial, it's important that MJ, this projector here, MJ and J, doesn't commute with the UJ. Because if they commute, basically it means that the action of the unitary operator on this MJ is trivial, and the final result is just a unitary operator living on the original hyperspace of the system, which is trivial. Like if you have a state and you perform a unitary operation, the entanglement doesn't change. The relations will you rotate, I don't know, X in V, like you rotate some observables, but this doesn't really change the inferred physics of the electricity. And okay, let me break down explicitly what is the measurement operator that we are applying. So the measurement operator basically is given by maybe let me write sorry. So we have that slide N is I posso select a specific outcome that we denote as N. So we have N acting on side A, so this is my post-measurement state. And the measurement operator is basically this object here, where you see U lives in the hyperspace of the ancilla tensor product resistant, because it happens in both system and ancilla. And then we take the expectation value of this unitary operator between the ancilla degrees of freedom and the measurement outcome, and these states both live in the ancilla hyperspace. So this operator lives in the hyperspace of the system. Okay, so this is my the real post-measurement operator. And,
sorry, U is the product of all the UJs?
Yes. So already from that, from this expression here, you can see that this measurement operator depends on many things. Like it depends on the measurement outcome. It depends on the specific form of the unitary operator that you are choosing, and it depends on the auxiliary degrees of freedom. So in general, we have a lot of freedom to create the measurement operator that we want. And the simplest example that one can choose is the case in which psi of A is a product state. So psi A, product state. And for instance, suppose that it's a product state in the Z basis. Then the object here, and U psi A, basically factorizes because it's the product of MJ, UJ, VJ. In general, this is not true that if psi of A is an entangled object, there is no way to factorize it as a result. But the regime in which psi of A is a product state, then everything factorizes. And for instance, if we choose UJ to be e to the minus I u O on the system and Y on the ancilla. And then we measure in the X axis, so this MJ measure in the X axis. So now we will compute Xj e to the minus I u or j y j a. Remember that X is if we choose 0, just a simple state. X is 1 plus 0 divided by 2. If you want to write the next operator, it will be written as 1 plus 0 divided by 2. And each of these exponential can be written as the same thing that I was doing before, cosine plus I sine. So we have xj, which is cosine of u, I, oj, sine of u, yj. Okay, and as I said, x is 0 plus 1 divided by square root of 2, so it means that so the cosine of u gives a non-zero value just when we overlap 0 with 0. So we get the cosine of u divided by 2. And this object here is non-zero when basically y acting on 0 gives